OK，事情OK， Oops， 唉，等一下啊。哎呦，等我一下啊，把它移除掉。好，来。OK， 我们可能用话术讲一下。Okay, we have next one presentation. Also, she present in the Chinese. Okay.
我的题目是那个日本的关东大地震。它时间是发生在2011年的3月11号，星期五，日本当地时间是2点46分。那发生在仙台的东部，大概70公里的地方，深度达到29公里。那我们又可以称作它，除了311大地震，又叫做日本关东大地震、东北大地震。这是一张板块图。那右边浅色的是陆地板块，左边比较深色的是海洋板块。那他在说地震发生的过程，就是当其中一块海洋板块潜入到陆地板块之下，它中间摩擦的过程，当它的情形越来越挤压的过程中，就会发生地震。它的字跑掉了。然后右边这张图是美国的海洋研究局，他们预测海啸会到达的时间。然后是什么原因会造成海啸？就是当地震发生的时候，海底的地形突然之间的改变，会引起这个海水很巨大的波动。那到岸边这个波长越来越小，速度越来越快，就会引发海啸。看样子下面看不太到。那这是目前我们可以预测海啸的方式，就是说我们利用地震台跟潮汐台去知道说我们海浪现在的变化，还有我们目前知道我们什么时候会预测到地震的震度。那这个研究的人员会有一个手表，就是说当震度达到7.5度的时候，这个手表会发出警报。那研究的人，因为他们不可能无时无刻都坐在研究台上面去观测，他们只要发生的时候，他们就会马上知道。那我们能够预知地震吗？目前来说没有办法提前知道说，明天会发生地震，或是下礼拜会发生地震，所以我们只能大概提前几分钟的时间去争取这个可以疏散的时间。然后这个就是地震的 地震仪的那叫什么波吗？然后右边这张图就是每次，日本现在也是用这个方式，就是台湾也有，就是每次只要地震之前，我们都会收到，不是地震的前几分钟吧，可能1-2分钟，我们会收到这个简讯，然后你就会知道说，哦，有地震。可是通常我们收到的时候，就是已经发生完地震了，对。还没。那我们能做的就是，我们可以加快这个我们收到讯息的时间，因为每次就是真的收到的时候就，明明就地震已经发生完过5分钟10分钟，然后才收到这个简讯，我们就是收到的讯息不够快，然后或者是去开发其他的侦测地震的方式，这样子。
Okay, thank you. I would like to check that. Okay. In Taiwan, we have earthquake warning system. I don't know. In France, do you have that? Really? Oh, someone said yes. I don't know.
There's volcanoes, and so they use the earthquake system to predict if the
volcano. Okay, okay. But in the Taiwan, it is very difficult for the pre-warning because the Taiwan is so small, and we just located in a plate, right? So when there's the epicenter of the earthquake is too near sometimes it's just close to the Taiwan, and sometimes it's just located on the island of the Taiwan. So I think this is very hard to have a pre-warning. I mean, the pre-warning may be larger than the 30 seconds or even to the 1 minute for you to the application to anywhere. But in Taiwan, I think it is very hard for the pre-warning of the earthquake. But however, sometimes we can get this kind of the message, SMS message through your cell phone from the government. Okay, so I think right now the information is very, very ideal and very quickly for you to understand it. Okay. Okay, by the way, I need, because right now I'm checking your homework, so I need to your group member list because I forgot. So maybe 你可以帮我就是让大家写一下，有没有一张纸可以让大家写一下 ？OK， 有没有同学有纸？So please help me to sign your name and your ID. So in the last time, this is number 1 group. 1, 2, 3, 4. Right. Okay. Okay, next I would like to show you we just present the idea of the PM 2.5, how to detect the particle, right? And so I have the source here and the refraction of the optical light. Okay. We also can be used in a smoke sensor. Okay, either. So you can find here, this is the source of the light, and this is the reflection because of the smoke. So in your house, right now in Taiwan, we can get a free one in your kitchen or in your any place in your house from the government. So I can get a free one of the smoke detector. And there's another fire. I mean that sometimes you can find this smoke detector and another detector. The other one will be a flame detector. It is based on the spectrum of the light. Okay, for sometimes we may hear the visible light between this spectrum, and sometimes we will hear the near infrared or the far infrared because this is the have a larger wavelength of the optical. So based on this spectrum, we can detect maybe the fire because the light spectrum of the fire are located in the large wavelength. 怎么了？没事哈。Okay. So I think the same idea right now. Every time you get into the building, someone will use the infrared camera or the sensor to check the temperature, right? So this is based on the infrared radiation. It is also belong to the optical instrument. And for the infrared radiation, we will have a passive and the active one. What is the passive? Passive means that the detector just receive the radiation from the target, but the active one sending a source to the target and receive the refraction of the infrared spectrum. Okay, so this will be the source and the refraction. So this is the active, and the other one will be just receive the source. Okay, so this is another way. Okay, and the next I would like to show you also an optical fiber sensor. Okay, I think maybe some of you already see the very small, very like your hair, a very small fiber. Anyone see that before? Okay. And sometimes it is usually used for the data transmission, especially for the internet. Okay, because it can be transmit very large data. But somehow we can use this kind of the fiber optical sensor to detect the environment behavior. Okay, and here this is some advantage of the optical fiber sensor, because this is the lightweight and all passive, and EMI resistance. What is the EMI? It is electromagnetic wave interference. So each time in the movie, you will see, oh, if I need to shut down the robot, I need to trigger a EMI weapon, right? It is electromagnetic pulse to destroy all the the electrical equipment or the robot. Okay. Does someone ever see the Matrix before? No? Matrix. Matrix 1, 2, 3. Anyone? You? And another? No? 都没有人看过 One? Yes, yes. So you know what I'm talking about, the EMI pulse, right? Because there's they driving the spaceship as a lot of, I don't know, the robot and come in and need to trigger the EMI. Okay, thank you. Okay, so the fiber optical is very good to detect the EMI, and also it is the multiplexing potential. Okay, I would like to show you next. The famous one is one of the optical fiber sensor is the FBG. The full name is the fiber black grating. So what is that? The FBG is the similar type of the strain gauge, but in terms of the fiber optical. Okay, how can I say that? Because I used a laser to have some gate of the fiber. If I have a strain, maybe extension, the spacing, the original one is L, the extension one is L prime. The spacing extended, right? So for the input source of the light, I can get a response of the wavelength, a peak one. This is the original one of the wavelength. But however, if I have to extend the spacing of this FBG, so you can find there's a shift of the peak of the wavelength. So based on this idea, I can check how much of the change of the wavelength and how much for the spacing, for the delta L. Okay, so this is the basic idea of the FBG, fiber black grating. So if you use this and replace the electrical strain gauge, okay, just as I said, I have an electrical strain gauge like this one. I replace this one, so means that I can use the fiber up black grating FBG for all kinds of the transducers, right? I can use this FBG for the pressure, displacement, and also the temperature. For any kind of the sensor we can use. Okay, and one advantage of the FBG sensor is that I can use the several FBG. You can find in this optical, I installed several FBG just using a single optical fiber. Okay. So this is a very useful, because for the previous sensor, just the the strain gauge. So I need a cable, and I also need this is the V in, and this is the V out. So I need a cable for the power supply, and I need a cable for the signal observation. So means that for each sensor, I need a cable, one cable. So of course, if I have only a borehole like this one, maybe this is the 7 centimeter in the diameter traditionally. This is the borehole size. And in this borehole, I try to monitoring. Maybe in the Taiwan, we have a very unique geological condition. So maybe in this borehole, I need to monitoring maybe more than 3 confined water pressure. So this is the first layer. second layer, and the third layer. I need to install a sensor here to monitoring the water pressure in a confined aquitard or aquifer, right? But you can imagine that if I have a cable, one cable have a 1 centimeter diameter like this pencil, and I have a 3 in a one borehole, maybe this is, I think, okay for the installation. But however, if I try to monitor more than the 5 and more than the 10, you can imagine that in a single borehole, maybe there is 10 cables for the sensors respectively, right? So it is not easy for, because I would like to say, drill a borehole is very expensive. So that's why I need to reduce the number of the borehole and increase the number of the sensor at all, if possible. But however, you can find if I just can put only maybe 4 or 5 sensors because of the size of the cable. Maybe I need a lot of budget to finish the monitoring. But however, if today I already have the FBG technology, means that I can use only one single transmission line, and for the multiple sensor, or maybe more than 10 and even to the 20. Okay, so this is the advantage of the FBG. Advantage of the FBG at all. Okay, so that's why the FBG maybe in 10 years ago it is very popular for the field monitoring. But I would like to say in the maybe 10 years ago the FBG does, I mean, they still have the main system to get the source of the optical fiber and to find the response. Just as I say, you need to find the peak of this response. But I would like to say this is the very sensitive one because the wavelength is very small, right? It may be like the micrometer or the nanometer scale or nanometer scale. Okay, this is the, and this is the power -1. So it is very small one. So I need a very good system to distinguish the difference of this wavelength. So in 10 years ago, maybe the main system of the FBG, I mean to send the light source and to analyze the response of the wavelengths are very expensive. Maybe more than in the 10 years, 20 to 10 years ago, maybe how much? $100,000 USD for this equipment. Okay, so expensive. All right. So however, right now is, I think, down to the 30,000 USD, but still very expensive. But I think right now we can use this FBG for the more application in the field. And the next, I would like to show you the advanced technology of the optical fiber sensor. Okay, so right now we just show you FBG. The FBG, like the strain gauge, it is using a laser to get the gate okay, and get the response of the different wavelength change. But however, right now, because the advance of the technology, we can use the original fiber sensor without any modifications, only original fiber sensor, and with a different kind of the principle, Rayleigh wave, Raman wave, and Bolin wave, we can get a different application. For this one, this is the Rayleigh wave for the OTDR or the FDR, okay. And for the Raman and the Bolin, BOTDR, BOTDR. Okay, let me show you, because this is you need to take a course of from the double E or optical sensor. So I would like to show you, this is just because of the different spectrum. In this one, this is the frequency. Okay, with the different frequency, the highest one is the Rayleigh one, and the next one is the Bolin, and then the lowest one is the Raman. Okay, so for the Raman, you can use the optical fiber sensor directly to detect the temperature change. Okay, means that I put the optical fiber maybe in this roof, I can check the temperature change at all. And if you use a Boolean type, I mean much higher frequency of the optical source, you can check the strength as well as the temperature. Okay, so for this is the mostly for the BOTDR to monitoring the strength. Okay, and for the highest one, the Rayleigh wave. If you use the Rayleigh wave principle as a source to the fiber to the optical fiber, it can be detect the dynamic strength for the in the field. So for this kind, right now it is for the seismic measurement. Okay, in the US right now they use this kind of the optical fiber sensor for the earthquake monitoring. Okay. So right now this I would like to say this is what we call the distributed fiber optical sensor. We don't need to take any modification of the fiber optical sensor. We just use it on and give the pulse and detect the refraction based on the different frequency. So if you use the Boolean, you can check, just as I say, you can check the strength. You can check the strength at all. Okay, so this is the BOTDR analyzer, and we can check the strength distributed in a very long distance. For this kind of application, I can put the optical fiber sensor along maybe the trail, okay, or the building, or anything else you try to monitoring more than the 100 kilometers. Okay, and this is distributed. But however, I would like to say the spatial, the spatial resolution, maybe 1 to 2 meters. I mean, each 1 meters, I can get the strength. And the next 1 meter, I can get another strength. So this is what we call the distributed sensor. Okay. And another one is the OTDR. Okay. This is the source. And if I have some deformation of this fiber optical, I can get the response here. So I can know where is the strength and where is the deformation at all. So this is the what we call the BOTDR or the OTDR. Okay. So far, so good. So just I say, I can put the distributed acoustic sensor, okay, into the maybe the pipeline. This is the pipeline, gas pipeline, or the oil pipeline, or some the boundary. Okay, so I can very easily understand if there's any, I mean the leakage for the temperature or the strength. Okay, I can get the variation very quickly based on this distributed acoustics sensor. But I would like to say, okay, let me finish this one. And for the higher is the frequency, just as I said in here, if I use the radio wave, I can use the fiber optical sensor. Right now, they call this is the dark fiber for the seismic measurement. Okay, so this is the, you can find this is the more than the 400 meters, and each sensor have their own vibration records. So I can understand the seismic from the earthquake. Okay, so this is just maybe in this recent 5 years technology. But I would like to say the main analyzers of this kind of the distributed fiber sensor. For the previous one, it is the 100,000 US dollars. But right now, I would like to say this is the very expensive. Very, very expensive. Okay. Okay, so this is the 300 and 1,000 USD dollar device. So you can see this cable can be also used for the borehole downhole the measurement. Okay, so this can be used for the earthquake monitoring. And also in the US, they also put this sensor because right now we have a lot of sensor for the communication, and this cable is the beneath under the sea. I just read the news that the Google have a cable directly from the US to the Taiwan. Okay, and this cable maybe most of them is the optical fiber. So they try to use this cable to monitoring the earthquake under the ocean. Okay. And also we can use this kind of the sensor to detect the landslide, just as you show on the friend's case. Okay, they put a sensor here. Okay, so I can detect the strength of the slope. So this is the strength from the top. I mean, this is the top view of this slope. Very, very interesting. But I'm not sure because it's still very, very expensive so far. Okay. And what is the next of the fiber of the optical sensor? Is using a satellite. There's several different kind of the satellite image we can use. Okay, So for the traditional one, we use the visible satellite image for the change of the large scale. I mean, this is a large scale. Right now, we have a radar. It is what we call the INSAR. It is just like the radar to detect the aircraft or some the airplane, but it is from the top to the ground, and we can use this radar for detect the displacement. Okay, for this one, this is what we call a D-INSAR. What is that? It using the two image in a different time. This is the radar image. So I gave the response of the reference. I gave the response of the reference. If this two image have the difference between the wavelengths, so we'll show like this one. This is what we call the rainbow contour. Each rainbow contour means a cycle of the wavelengths. So depends on your radar wavelengths. Maybe for most the INSAR wavelengths is like the 1 to 3 centimeters. So for this one, it means that each contour like the displacements more than the 1 centimeter. So I can use this contour to calculate how much difference, I mean the elevation difference between the first image to the second image. So this is the what we call the D-INSAR. And if I use several image based on this one, this is what we call the PSI INSAR. This is the persistent scatter INSAR. So I can choose a very good quality of the refraction, because in each time you don't get a very good quality from the refraction, because you know that if you have grass or the frost area, there is no response of the radar, because you have a radar from the top to the ground, but no refraction because of the trees, of the woods. But if there is a very, no woods, just the soil, or there's a house or some kind of the structures, so always have a very good quality of the refraction. So I can use that point for calculate. So you can find here in the left side, each point means that have a good quality of the refraction during the several pictures of the INSAR. So I can determine the displacement of this point maybe during 1 year or 2 years to see how much difference of the elevation change. Okay, so sometimes this is used for the landslide, also for the land subsidence or land subsidence. Okay, do you know what is land subsidence or land subsidence? In Taiwan, we have a very serious problem of the land subsidence. Land subsidence means that also this is our ground, and after 1 year, 2 years, 3 years, settlement, the ground surface settlement, because in the Taiwan, we use a lot of pumping water underground. So if you pumping the ground water, and if you already learned the principle of the soil mechanics, you know that the consolidation effect, and so the surface, the ground surface will settle down each year. Okay, so maybe later I will show you what is the condition of the land subsidence. Okay, so the land subsidence very can be captured very good by this kind of the INSAR radar. So the next, I would like to show you the radar instrument. Compared to the acoustic one, the radar have a higher frequency, that's all. So it may have a higher resolution, but the same idea, but with a higher resolution. So it can be divided into two. One is the non-contact, just the radar. And the other one is the cable, leading cable, what we call the waveguide radar. What is that? For your cable, like this one, or the cable from my computer to the projector. I need a cable, right? So inside we can send in a radar. So that's why we call the waveguide radar. And for this kind of the radar, we can use also using the Doppler principle for the water flow. Okay, the same idea of the ADCP. We just show you in the before. Let me show you. Go back. Oh. So you can find we already learned so much different kind of the sensor. So let me say again. In the beginning, I would like to introduce several kinds of the sensor for you, based on the different kind of the principle, because I want let you know what kind of the sensor in the future we can use. Because you need to understand, if you have a project for the monitoring, you need to understand first what kind of the potential failure mode, or what kind of the potential problem it is. And then we can choose an appropriate sensor or a good sensor for the monitoring. So that's why I trying to introduce so many kind of the sensors. And just as I said, for the acoustic one, we can use the Doppler to detect the water flow. And and for the radar, based on the Doppler, we can also use that for the water flow. Okay, so this is a fixed one, and this is a handset one. Sometimes it is used for the overspeed in a high speed way. Okay. And the other one is my research. This is what we call a TDR. Originally, this is developed from the 1960, and it is used for detect the cable default, like the telephone line or the power line. Because in that time, we need a device to understand where is the location of the failure. So then we can change the cable very quickly. And right now, we can use the TDR not only for the cable deformation detection, locating, like this one. We can also use for the interface. We will show you later. And also, if I use this for the open area, I mean not only inside of the cable, but also some of the conductor. I will show you later. And I can use for detect the dielectric property of the material. Let me show you. So here you can find, if I have the value of the cable, so originally there is no response. I mean the wrong response, because there is no reflection when I send in a radar. But if I have a value for the deformation larger and larger and larger, will have a reflection like this one. So if I have a time where it is, and I already know that the velocity, so I can determine the location of this. So this is what we call a time domain refractometry. Okay, using a signal capture from the time domain, we can get the location on this location.
What's on the y-axis? What's on the y-axis?
You mean this Y?
Yeah.
Actually, this is the voltage. But sometimes we change to the refraction coefficient from the -1 to the +1. Normalize. How can I say? Let me show you. Because this is in detail. This is the +1. This is the -1. Okay. If I have a cable and I have a radar transmit in this cable. So mostly it will be the 0, 1 because there's no refraction. But if I have a termination, mean that there's no more cable at all. So there's a totally refraction in the end of the cable. So in that area, we may have +1 refraction. And the other condition is that because somehow this is just the waveguide with the positive and the negative conductor. For the mostly, this is the cable with the positive and the negative, and we may have electrical magnetic field. But somehow, if I have open, just I said, open end, I have a total refraction. So this is the refraction coefficient 1. But somehow, if I have a shorted condition, means that these two connect together. What happened? No more signal will reflect. So they are going to the -1. This is the open case. And this is the shorted circuit case. So that's all. Okay, so that's why we're trying to divide it into the +1 to the -1. If you trying to understand in the detail, maybe I can give you more paper. Okay. But I would like to say the TDR will be like the GA nerve. The human nerve is a source to provide the radar, and through the nerve, we can detect the pain, the heart, the cold, weather. Okay. Also, for the TDR, it sends the pulse of the radar. So based on the different kind of the waveguide, we can use for the deformation, for the water level, and even for the soil water content. Okay. So let me show you a very good example in the Taiwan. This is the Lushan area in the Nantou. Have you been the Salmon Lake? Okay, no? Yeah. Near the Salmon Lake, if you there's one way to the Salmon Lake, but if you going up to the mountain area, there's Hehuan Shan. Okay, it's very famous because there's the only place more than the 3,000 meters, and you can easily get there by drive the car. Okay, so in the middle way of that, there is a place what we call the Lushan, and also famous by the hot spring in this area. Okay, however, there is a very big Kuruvian. What is Kuruvian? Is that a very old and already landslide slope. So there is a very large thick of the landslide. So in this area, we have a very large Kuruvian slope at all. So in that time, I drill a borehole 1, 2, 2, 3, 4 to monitor the stability of this landslide, because for this is more than 100 meters depth. So it's a very large slope. And for this area, you can find the green one is what we call the colluvian. Colluvian. Okay, I can email it, the paper I just published last year to talk about this case. For this case, I using a cable put inside of this slope and have a grout. And in 2007 and 2008, maybe 12 years ago, I'm so sorry. 12 years ago, how old are you in that time? 10? 10? Okay. So in that time, I installed the cable in the mountain area. And so in the beginning, it's just a straight line. But after, during the typhoon event, I can see a small refraction here. So means that there is some sliding surface underneath of this slope. So I choose this and determine the location of the sliding. So that's why I can maybe guess and predict the surface of the sliding. Okay, so that's why we use the TDR as a very good, very useful tool to determine the sliding surface. Because based on the engineering concept, we need to understand where is the location of the slope, a sliding slope. Because if I try to have some replacement or some reinforcement construction, like the soil nail or is the anchor, means that the anchor should be penetrate deeper than the sliding surface. That works, okay? Otherwise, not useful. Okay, so the determine the sliding surface is quite important for me. Okay, so this is another case. And this is the case for the bridge failed monitoring. Okay, so just I said, we can use the very simple cable attached to the bridge. And this is the, this is the 2 decks. And between these 2 decks, we have a fixer. This is the fixer like this one. Can be easily cut the cable. So if I can use this one, if there is a failure of the bridge, so I can use the radar and say, oh, oops, there is the open end of this radar. So I can quickly warn the passenger, no more get into the bridge again. Okay, so this is the final warning. The final warning before the bridge failure. Okay. Very simple idea, but just I say again, I show you some sensors, but you need to understand, can it be useful, especially in the field? Okay. Okay. Oh, let me show you a case, real case. I trying to, no, let me do it again. Sorry. Yeah. Let me get the voice. Okay. This is the place because this bridge, I'm trying to verify the concept of this one. The concept of the bridge value. So using the TDR, so you can find a signal, warning signal here. Sorry. Okay, warning signal here. Okay. At the same time, I also put another sensor. This is the second deck. So I can check the waveform and understand. So it is a final result of the cable with the open end. Okay, but I would like to say in that time, I also used a very simple, the switch. Okay, what is that? I just put a box and a wire and fix that when the wire is open that, so I can understand the switch is open, so I can know that the bridge fell. Okay, I also use this for the water measurement, water level measurement. Okay, for this is the cable, so I can understand where is the water level. Hello. Okay, and for this is the underpass. In Taiwan, we have several problems during the flooding, especially in the underpass. Someone died because they drive in the water and never can get out. So we need to understand the water level, especially in the underpass. And of course, this is another, monitoring for the field for the geotech measurement. I put a probe here in this section, but however, originally the cable has confined EM field, and this is for the parallel line, for the coaxial line. Oops. So you can find the EM field is confined inside of the cable or just surrounding the cable. But if I can use this kind of the sensor and with the conducted for this is the interface here. So maybe I can get a larger EM field. So at the same time, we can measure the outside material using the EM wave. So for based on this, okay, let me show you. I can determine the water content of the soil, and meanwhile, I can get the electrical conductivity, or maybe later I will discuss that with you. Also, the electrical conductivity of the soil. So I can monitoring using the. Also, I can combine it with this CPT. Do you know what is the CPT? So maybe later you can check by yourself. It's a cone penetration test. Usually it is to determine the soil frequency, friction angle. Friction angle. So you can check later, and you can penetrate automatically in the different depths to determine the strength, the shear strength of the soil, And this is for the another case. I've combined the TDR to measure the not only the water level, but also using the water content. I trying to find the mud flow and the stiff layer, because in the 2004, wow, 16 years ago, okay, in that time we have a very big typhoon event in Taoyuan. So you know that the Ximen Reservoir? No. Suggest you go there at least one time. It's a very beautiful place, and not so far, 40 minutes from here. Okay, maybe we can visit the Ximen Reservoir in our class. Okay, I can arrange that. Okay. So in the Ximen Reservoir in that time, 2004, we have a very bad problem, is that because there's too much the sediment from the upstream. In that time, maybe how many? 2600 mini tons or mini cubic meters of the sediment trapped in the reservoir. Okay, so in that time, the gate, this is the reservoir and the water level, and there is a gate for the hydraulic power supply. Okay, but this gate was buried from the mud and the sediment. So in that time, we try to determine where is the interface of this mud and how stiff it is. Because if it is too stiff, after too long, there's a concentration much higher. So maybe it is too hard to open the gate. Okay, so in that time, we're using a drill machine and combined with the TDR in this section, and also this is the DMT. Also try to measure the stiffness of the soil. Okay, this is the DMT. You can also try the keyword, and this is the pressure by the air to check the stiffness of the soil. So in that time, I combined these two sensors to check out the quality of the mud flow and the stiff layer, and make sure that the gate in here can be open or not. If cannot open, then we need to have some clean of this sediment advanced. Okay, so this is another problem. And also I use this kind of the penetrometer for monitoring the different depths of the water content. Okay, because this is used for the shallow landslide monitoring. Because in this area, maybe 1 or 2 meters, the stability is controlled by the water content. Okay, if there are much more water content, saturate soil may have a higher unit weight, but a lower resistance, shear resistance. So may we have a shallow landslide problem. So I use this to monitoring the water content. Okay, so this is the infiltration from the surface. So from the top layer, there is the change of the water content. But for the deeper layer, for this one, because the infiltration not so penetrate too deep. Okay, so they keep the same water content during the rainfall event. Oh, just I show you, this is the Siemens reservoir. This is the aerial picture. Okay, and this is the spillway. Oh, can you see that? So in the 2004 Aileen typhoon, we may have 27 million cubic meter sediment at all. So you cannot image how much it is, but you can say for a truck, maybe only 10 meters of the sediment, cubic meters of the sediment. So 27 million cubic meter of the sediment, how much trucks it is, okay? So in that time, you can see, originally this is the clean water, but after the Typhoon Aileen, this is like the muddy cake. We call it muddy cake. Okay, because there's too much sediment at all. And for that time, we have a power supply suspended more than 3 weeks, 70 days. And let me show you. Okay. So after that, we decided how can we do in the future? Because in the Taiwan, I think this is the common problem from the 2004 and the 2005. So there is a very important questions that how can we monitoring the suspended sediment from the upstream to the downstream? So I left the questions for you. Maybe next time we can discuss. You can find some newspaper regarding this issue in 2004. Okay. So any problem so far? So next, I will finish of this, and maybe we can discuss some application later. Okay. So see you guys next week.
Il est radical. Pareil.
Mm.
C'est quoi, dis-donc?